Okay, Assalamualaikum warahmatullahi wabarakatuh. This is tutorial for chapter 7, Entropy. Let's start with this first question, 720. Air is compressed by a 15 kilowatt compressor, 15 kilowatt, from P1 to P2. The air temperature is maintained constant. Okay, temperature is constant at 25 degrees Celsius during this process, as a result of heat transfer to the surrounding. So we have heat transfer to the surrounding, given the temperature of the surrounding of 20 degrees Celsius. Determine the rate of entropy change of the air. State the assumption made in solving this problem. Okay, let's try to visualize the system and process. This is a compressor. We have intake, that would be the inlet. And then we have the outlet. Okay, let's say that this is state 1 and this is state 2. Okay, there is a 15 kilowatt work in to run the compressor. Let's say that we put it here, work in 15 kilowatt. Okay, and of course we have P1 here, P2, which is not given. Okay, and we know the temperature remain constant throughout the process. So we say T1 equals to 25 degrees C, T2 equals to 25 degrees Celsius. Okay, no change in the temperature during the process. And we know that the T surrounding, okay, let me just state that T surrounding is 20 degrees Celsius. So basically that would be the situation that we have. Okay. All right. So assumption mentioned there, state the assumption made in solving this problem. So let's identify some assumptions so that we can simplify the problem. Okay, of course, first we assume what we call that steady. Okay, so there is no change in terms of when we talk about the energy balance, no change of energy in the system. Also, since we consider this as small, and since it is also steady, the kinetic energy change. Okay, let me put change. And since we can consider the compressor to be relatively small and horizontal, so this one we can assume to be also negligible, 0. Okay, and the medium is air, so let's assume this to be ideal gas. Okay, and also very important for our in chapter 7, then we assume no irreversibilities, because we are not given any information about the irreversibilities. So during the process, so we can say no internal irreversibility is okay during the process. Therefore, since temperature is constant, therefore what we are saying that our process or our system, the process is internally reversible, isothermal. Temperature is constant, isothermal process. Okay, so basically that summarizes the assumption that we are making. Okay, to solve this problem, let's start here. Recall that ideal gas, in ideal gas, the internal as well as the enthalpy is only dependent on temperature. So we can say that H is only in terms of as a function of temperature. So since temperature is constant, therefore we are saying that this is also very important. Since temperature is constant, doesn't change, and enthalpy is only change or as a function of temperatures, then we can say that H1 is equals to H2. Okay, let me state here, since T1 equals to T2. So constant temperature, so we're going to have constant enthalpy. And this is only true for ideal gas, okay, based on that assumption. Okay, so from there, then energy balance. We can state the general. We are talking about, this is kilowatt. Okay, so in terms of this one should be dot. Okay, rate. Okay, E dot in minus E dot out should be equals to the change of energy in the system. Okay, since we assume steady, then we know that you can eliminate that to be equals to 0. Therefore, rearranging this, E dot in equals to E dot out. Okay, so let's look at the system again. Energy coming in, we have only in terms of work. Okay, so W in dot. Okay, what about the one going out? I did not put here, but when we look at the question again, then heat transfer to the surroundings. So yeah, I think we should include here also. Heat is transferred to the surrounding in order to maintain the temperature in the system. Okay, so there is a heat transfer or Q out there. Okay, let's be more specific. So energy out is in terms of heat transfer only. Q dot out. Okay. Again, looking at the system, then these are the only energy transfer that we have. Okay, work going in as well as Q going out from the system. So having that, then we know we know this value work in given already 15. Therefore, our Q out dot is nothing but 15 kilowatt. Okay, based on the energy balance. All right. So having that value, then finally, then we can solve. We are asked to find the rate of entropy change. Therefore, the change of S dot is nothing but equals to minus Q out dot over temperature of the system. Okay, negative indicating that we are what we call that, heat is going out, so entropy will move out from the system. Okay, therefore just substitute minus 15 kilowatt and temperature of the system 25 degrees Celsius, but remember T here is in Kelvin, so you have to convert to Kelvin. 273 plus 25 Kelvin. So if you solve that, you'll get 0.0503 kilowatt per Kelvin. Okay, that would be the rate of entropy change in the air. Okay, that would answer this question. Okay, now let's move to the next question. 731. The radiator of a steam heating system. Okay, we have steam heating system. Okay, has a volume of 20 liter. Let's just draw while we read. Okay, let's say that we have a radiator, okay, of our steam heating system. Okay, we know the volume is 20 liter. 20 liter. Okay. Superheated vapor. Oh, yeah, superheated water vapor. So we know that it is in superheated condition. Okay, at least the initial state. 200 kilopascal and 150 degree Celsius. Okay, so 200 kilopascal, 150 degree Celsius. Okay, at this moment, both inlet and exit valve to the radiator are closed. Let's say that we have, of course, radiator, we're going to have the working fluid coming in and working fluid going out from the system. Okay, this is in and out. But mentioned there at this particular instant, Okay, at this moment, both valves are closed. So there is no flow in and no flow out from the system. So we can consider this as a fixed or rigid body then. Okay. After a while, the temperature of the system dropped to 40 degrees Celsius. So we can say that we can here T1 is 150 degrees Celsius. Okay. Then after a while, then the final temperature T2 is 40 degrees Celsius, okay, which is the room temperature. So you can also indicate the surrounding is equals to 20 degrees Celsius. Okay, as a result of heat transfer to the room, okay, we can also put it there, okay, as a result of heat transfer from the radiator to the surrounding. Okay. Determine the entropy change of the steam during this process. All right, state one, we know that T1 is 150, P1 is 200 kilopascal, and even mentioned there superheated vapor. Okay, superheated. We know state one already. We are not sure about state two. Pressure is not mentioned that it will be constant, no, but we know that it is a fixed, what we call that, tank, or well, basically rigid tank in this case, since there is no mass flow in and out at this moment. So we know with this, then we can say this will be our relation. Okay, the specific volume will be constant. Okay, so in this case, then this is the information that we have. So let's look at and solve this problem. So at 1, which is the initial state, okay, we can refer to table. This is steam. So let's go to table, steam table, but we know already is given that it is superheated. Superheated 200 kilopascal, which is 0.2 megapascal. So this will be the table. We know that saturated temperature is 120, 21, and our temperature is 150. So we have already 150 there. So at 1, table A6, which is superheated. If you refer to the table, okay, for P1 equals to 1, wrong. Okay, let me erase that one first. P is 0.2, 0.2 megapascal. P1 equals to 150 degrees Celsius. F, you can see in the table. Then V1, specific volume, is 0. You do not need to interpolate this. It's already there in the table. So 95986. 95986 meter cube per kilogram. And you can also find the entropy S1, which is 7.281. 2810 kilojoule per kilogram Kelvin. Okay, this is straight from the table. All right, we need this because we know that the state 2 is related based on the volume, specific volume. Then okay, at 2, okay, so what we know is that T2 is 40 degrees Celsius, and V2 is equals to V1, which is equals to 0.95986. Okay, let me skip the unit. You can see from top there. Okay, so we are not sure what state it is, so we need to check. If you go back to the table, we have V equals to 0.95986, temperature 40. So let's go back to the table. Let's go to the A4. Okay, as usual, then first to check the condition, go to the saturated table. We know temperature is 40, so yeah, we have 40 there value. And VF is 0.001008, okay, which is low, smaller than the V. And Vg is 19, which is larger. So yes, we can expect that state 2 will be in the saturated mixture region. Okay, so taking from there, then, okay, let me go back to the slide. So from there, then you can see from table A4, okay, you have VF equals to 0.001008, okay, and VG is 19.515, okay. So we can find the quality. Remember, we have the relation V2 is equals to VF plus X VFG. So X is just nothing but X is equals to V2 minus VF divided by VFG. Okay, so these are all values. You just substitute. V2 is 0.95986. VF already from the table. VFG is nothing but VG minus VF. So if you do that, let me just rewrite just for the sake of completeness. 0.95986 minus VF, which is 0.001008, okay, divided by 19.515 minus 0.001008. So if you do that, then you get X to be equals to 0.04914. 4914. Okay, you can check the calculation. So this is our X value. Okay, so knowing the X, then you can go back to the table. You can find SF and SG or SFG. So you can just calculate for S2. Therefore, S2 is nothing but, remember, the equation will be SF plus X SFG. And you have all the values from the table. Okay, which is 0.5724. 5724 plus X is 0.04914 and SFG from the table is 7.6832. 7.6832. Okay, so if you solve this, then you have S2 is nothing but equals to 0.9499. 0.9499 kilojoule per kilogram Kelvin. Okay. All right, so we have the entropy for state 2. We need to find the entropy change. So, yep, we are given the volume, so we can find the mass. Okay, mass M is equals to volume divided by the specific volume. Okay, you can use the first state. Volume doesn't change, 20 liter. Okay, using the first state, then you know that this is 20 liter. To convert into meter, then we know that 1 meter cube is equals to 1000 liter divided by V1 already from there. Yeah, V1 and V2 is the same anyway. 0.95986 meter cube per kilogram. So you will cancel meter cube, liter also cancel. So you end up with only kilogram, which is the mass. And that will give you 0.02084 kilogram. Okay, so that will be the mass. Now everything is known, therefore you can complete the to answer the problem. Okay, this is capital total. Okay, which is mass multiplied by the specific entropy, S2 minus S1. Mass is already given there. We calculated 0.02084 kilogram. And S2 as calculated just above 0.9499 minus S1 is 7.2810. 7.2810. Okay. And the unit for this is kilojoule per kilogram Kelvin. So kilogram you can cancel. So you end up with the unit of kilojoule per Kelvin. And if you do that, the calculation, you would expect that will be the negative value. So you'll have minus 0.132, 0.132 kilojoule per Kelvin. Okay. The minus indicating that your entropy is reducing in the system, in the rigid tank or in the radiator. Okay, because heat entropy is transferred through the heat to the surrounding. All right. So let's go to the next question. 737. We have refrigerant 134A. Okay, that is our working fluid now. R134A. Expanded isentropically. Okay, isentropically, we know that this means that the oops. Okay, I click the wrong button. Okay, well, we finish this. Let's go to this. Okay, isentropic meaning that S is constant, equals to constant. Okay. Erase this. Oh, already saved, so I cannot do anything on that. Okay, fine. Okay, from we have a 600 kilopascal, 70 degrees Celsius at the inlet of a steady flow turbine. Okay, now we have a turbine. Okay, 200 kilopascal at the outlet. So let's draw our turbine. Turbine goes this way, expanding. Okay, compressor goes the opposite way. Okay, so we have inlet, that is state 1, and then the outlet, state 2. All right, and we know that at state 1, we have P1 equals to 600 kilopascal. T1 equals to 70 degrees Celsius. Okay. At the outlet, we have P2 equals to 100 kilopascal. Okay, what else? Okay, I think that's all that we are given. Oh yeah, we are also given the outlet area. Outlet area A2 is 1 meter squared. We are also given the inlet area A1 equals to 0.5 meter squared. And then we are given the mass flow rate, okay, m dot is equals to 0.75 kilogram per second. Okay. All right. And also we mentioned that already, isentropic, so S2 equals to S1. Okay. So this can describe the process. Isentropic. All right. Okay. Calculate the inlet and outlet velocity when the mass flow rate is 0.75. Okay, so let's check on the condition. We are not given any information about this state. We know that it is R134A. So let's go to the table for refrigerant, which is saturated for R134. Let's go to A11. We are given let's go with the pressure. Okay, so A12. If we go to A12, we know it is 600, okay, 600 kilopascal. The saturated temperature is 21.55. Okay, so let me just write from A12, okay, P1 equals to 600 kilopascal. T saturated was 21.55, which is less than the T2. Oh, sorry, less than T1, not T2. Analyzing the first one. Okay. So what does it say? What can we conclude? For pressure, the saturated temperature for that particular pressure is less than the temperature of your state. So therefore, then we can conclude that, therefore, superheated vapor. Okay, vapor. All right. So if you are confused with this, then try to plot the PV diagram. If you plot the PV diagram, okay, PV diagram, the saturated table. Remember, the constant temperature is going downward. Okay. Okay, you can check for that particular pressure. Okay, if the saturated temperature is this, okay, if the temperature is higher than the saturated temperature, it should be in this region. Okay, superheated vapor. All right. Okay, so since we know that this is superheated vapor, so we go to next table, table A, A13. So let me start here again. At 1, okay, state 1, we know that P1 equals to 0.6 megapascal and T1 equals to 70 degrees Celsius. Let's go to the table. It's my table, okay. So we go to this table, 0.6 megapascal, 0.6, this is 0.6 megapascal, refrigerant 134A. And for temperature 70, yes, we have temperature 70 there. So you do not need to interpolate anything. So you can just take all the information from there. And yeah, saturated temperature to 1.55, as discussed earlier. So just take the value from there, from table A13. Table A13. So if you do that, then you have S1 equals to 1.0705 kilojoule per kilogram Kelvin. And V, okay, is 0.043 4069. 43069, yes. Okay, meter cube per kilogram. Okay, you can refer to the table. All right, so we have these two information. We need V because we need to find velocity anyway, okay. We need S because we know S2 is equals to S1. So then this will be the information to get to our state 2. Okay, so at state 2, okay, we are given the pressure, which is P2 equals to 100 kilopascal or 0.1 megapascal. Okay. And then S2 equals to S1, which is equals to 1.0705. Okay, unit kilojoule, kilogram, Kelvin. Okay. So let's check. Are we still in the superheated or is already in the what we call that, mixed region? Okay, if you go back to the table, you can either use 0.1, go to 0.1, table A13, okay, pressure equals to 0.1 megapascal, and see whether your S is within somewhere. Okay, S is 1.0705. S is, yeah, somewhere here. Okay, it is still in superheated region. 1.07, so we have at 10 degrees Celsius, 1.0628, and at 20 is 1.0918. So 1.07 should fall in between these two values. Now we have to interpolate. Okay, so this is the table to refer. So we know that we know, let me just put it here. It is superheated, still superheated region, superheated vapor. Okay, but then we have to interpolate. So from the table, what we have is T, S, and V. Okay, if you get from the table, remember it falls in between temperature of 10 and 20. Okay, this is our T, which is T2. Okay, we are not interested on finding that T2 anyway, but anyway, let's just put it there. 1.0628, this is from the table. Okay, this is what we have, 1.0705, 0705. So from the table for 20 degree is 1.0918. We are interested in the V, 0.22506, 0.22506. This is our V2, which we want to find out. And for 20 degree, 0.23373. Okay. So you can use this in order to get V2. Okay. If you remember the relation, V2 is nothing but equals to, well, yeah, okay. I'll just, basically, V2 minus this divided by this minus this equals to now 1.07 minus 1.06 divided by 1.09 divided by 1.06. Okay, so let me just rearrange. After the rearrangement, this is what you should be getting, 0.22506, okay, which is this, plus, and the ratio, okay, 1.070, 1.0705 minus 1.0628 divided by 1.0918 minus 1.0628. Okay, that is the ratio of this. And the denominator of this, bring to this side, you will multiply 0.23373 minus 0.22506. Okay. All right. So that would give you, if you do this, if you are confused, just go back to the interpolation basic relation. Then you rearrange, you'll be getting this. Okay, therefore your V2 would be equals to 0.2274 meter cube per kilogram. Okay, that would be V2. Now we have V1 and V2. Therefore, you can complete the problem to find the inlet velocity. V1, which is the velocity, is nothing but equals to m dot, where the specific velocity V1 divided by the area A1. M dot is already given from the problem, okay, 0.75 kilogram per second. V1 we got already from table A13, and A1 also given. So if you substitute everything, you have 0.75 kilogram per second multiplied by V1, which is 0.04, 0.04, 3069 meter cube per kilogram, divided by A1 is 0.5 meter cube. So meter cube will cancel, kilogram will cancel. Oh, sorry, this one is area, meter squared, not meter cube. Yeah, otherwise then you don't have that. This is meter squared, and you should not be cancelling all the meter there. Area is meter squared, and this is meter cube. So you will cancel the whole thing of this with only two of these. Okay. Kilogram and kilogram will be cancelled, so you will end up with meter per second. And that will be, for V1 is 0.0. That's okay. 0.0646. 0.0646 meter per second. We can continue with the outlet velocity. Velocity, okay, which is V2, same mass flow rate because we have only one inlet and one outlet. We have specific volume for state 2 of the outlet, and we have also the area of the outlet, which is 0.75 kilogram per second multiplied by, we calculated already, 0.2274 meter cube per kilogram, and all divided by 1 meter squared. 1 meter squared. So again, we cancel this. Kilogram also cancel. So if you do that, then you get 0.171 meter per second. Okay, so basically these are the answer. Okay, I think that would be all for this part. Okay, okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.